something that has...
Quantum computing is a fundamentally new model of computing with many unique challenges and opportunities to impact a broad range of applications.
It can perform a computation in seconds, what would take the world's fastest supercomputer years.
In 1946, with ENIAC, ENIAC marked the beginning of the digital age, the first general-purpose electronic computer. And yet, without even knowing it, ENIAC had launched the greatest technological revolution in human history. It introduced something deceptively simple, binary, zeros and ones, a language every digital device around you still speaks today. Then came the milestones that reshaped human progress. UNIVAC brought computing into commerce. Intel's 4004 shrank it to a microprocessor. The Apple, I gave it a face. Google gave it knowledge. Mac OS X made it beautiful. For decades, progress was linear, smaller chips, faster speeds, smarter software. But in 2019, something broke the curve. Google's Sycamore quantum processor completed a problem in just 200 seconds, a problem that would take the world's fastest supercomputer over 10,000 years. That's not just a difference in speed, it's a leap into an entirely different reality. And make no mistake, quantum computing isn't just fast, it's precise, with high accuracy, where problems once thought unsolvable suddenly aren't. The quantum race is already well underway. Google, IBM, Intel, D-Wave, Microsoft, and China's quantum labs, all pouring billions into turning decades of theoretical physics into working quantum hardware. The question isn't whether quantum computing will transform our world. That's inevitable. The real question is, will we be ready when it does? Classical computers run on bits, zeros and ones, but we're reaching their limits. Moore's law is slowing down, and transistors are now just 3 nanometers wide. At that scale, quantum effects start to take over. Electrons tunnel through barriers, making traditional logic unstable. Building smaller now means working with atomic precision. That's where quantum steps in, not to replace classical computing, but to do what it never could. Consider a global logistics giant, Omniship Global. They operate a fleet of 500 cargo ships, 2,000 aircraft, and 10,000 trucks moving goods for over 100,000 clients. Each day, they face billions of possible routing combinations, and any small inefficiency cascades into massive losses. A classical optimization algorithm, even on a supercomputer, might take weeks to find a near-optimal solution for just a segment of their network. And by then, the conditions have already changed. Studies from companies like IBM and Google estimate that a mature quantum computer running a sophisticated optimization algorithm could analyze Omniship Global's entire logistics network in minutes. This isn't just about saving time, it's about unlocking massive efficiencies. Imagine reducing fuel consumption by 15 to 20% annually, translating to billions of dollars in savings and significantly lower carbon emissions. Decreasing delivery times by an average of 10 to 12%, enhancing customer satisfaction and enabling true, just-in-time global inventory. This isn't just theory. Companies like Mercedes-Benz, Volkswagen, and JP Morgan Chase are actively investing in quantum research, specifically for these kinds of optimization challenges. They see the writing on the wall. The company that masters quantum optimization first gains an unparalleled competitive advantage, reshaping not just their industry, but potentially the very flow of global trade. And that's just one example. Quantum computers aren't just fast. They unlock efficiencies, enhance security, and redefine what's possible. So, how does this new kind of machine actually work? Traditional computers use bits, 0 or 1, simple. But quantum computers? They use qubits, and qubits don't follow classical rules. A qubit exists in something called superposition. Imagine a coin that's not just heads or tails, but somehow spinning in midair, representing both possibilities at once. It's only when you measure it, when you look at it, that it collapses into a definite state. And this is where quantum computing gets its power. One qubit can represent both 0 and 1 simultaneously. 2 qubits? That's 4 possible states at the same time. 3 qubits, 8 states. The pattern keeps growing exponentially. With just 300 qubits, a quantum computer could theoretically represent more states than there are atoms in the observable universe. But superposition is only part of the story. There's something even stranger, called quantum entanglement, a phenomenon so bizarre that Einstein famously called it spooky action at a distance. When 2 qubits become entangled, they're no longer independent. They form a single quantum system where measuring one instantly affects the other, even if they're separated by light years. No signals, no delay. So how do quantum computers actually compute? They harness the strange power of quantum interference. Some possibilities amplify, while others cancel out. A well-designed quantum algorithm doesn't brute force every solution. Instead, it guides the quantum system toward the right answer. In simpler terms, while a classical computer checks each possibility one by one, a quantum computer explores all possibilities at once. Then, through interference, the wrong answers cancel out, and when we finally measure the result, physics itself reveals the most likely correct answer. It's like having a million classical computers working together in parallel. But here's the catch, and it's a big one. Quantum systems are incredibly fragile. A single disturbance, a stray photon, a slight temperature change, even the faintest vibration can cause decoherence. That means the quantum state collapses, and all that quantum advantage? Gone. That's why quantum computers need extreme environments. They're kept in shielded chambers to block out electromagnetic interference. They're cooled to temperatures colder than outer space, fractions of a degree above absolute zero. It's like building a symphony with instruments made of mist. Different companies are betting on different approaches to solve these challenges. Google and IBM are using superconducting circuits. IonQ and Honeywell trap charged atoms in electromagnetic fields. Xanadu is working with photons, actual particles of light. Microsoft is pursuing something even more exotic, topological qubits based on theoretical particles called anyons. Each approach has its strengths and challenges, and no clear winner has emerged yet. So, what can quantum computers actually do today? They're not replacing your laptop anytime soon, but they're already showing promise in specific areas. They can simulate molecules for drug discovery in ways classical computers simply can't. They can optimize complex logistics problems across finance, supply chains, and energy systems. They could eventually crack or defend modern encryption systems. And they might supercharge machine learning by discovering patterns beyond classical reach. But where is all this leading? Who's in control? The race for quantum computing dominance isn't just happening, it's accelerating at a pace that's reshaping global power dynamics. In 2019, we witnessed a pivotal moment in this race. Google announced their 54-qubit Sycamore processor had achieved quantum supremacy, completing a calculation in just 200 seconds. That would take the world's most powerful supercomputer over 10,000 years. It was a watershed moment, one that signaled quantum computing had moved beyond theoretical physics into practical reality. But Google isn't alone in this race. IBM quickly countered with an ambitious roadmap, 1,000-qubit processors by 2024, scaling to 10,000 qubits by 2027, and potentially reaching 1 million qubits within a decade. They're not just building for performance demonstrations, they're architecting for scale, preparing for what they call the quantum era of cloud computing. Meanwhile, Microsoft is taking a different approach entirely. They're betting on topological qubits, a theoretically more stable form of quantum bits that could solve many of the field's current challenges. Then there are companies like IonQ and Quantinuum, refining trapped ion technology, where qubits are made from actual atoms, suspended by lasers. These aren't just quantum computers, they're quantum platforms, built for versatility and real-world applications. But while American companies make headlines with their advancements, China has been making remarkable progress, somewhat more quietly. They've already demonstrated quantum teleportation, over 1,200 kilometers, launched quantum satellites, and even achieved their own version of quantum supremacy. This explains why it's not just tech companies in the race. Governments worldwide are investing billions in national quantum initiatives. The United States passed the National Quantum Initiative Act, allocating $1.2 billion. China has its ambitious Quantum Internet Plan. Europe launched its Quantum Flagship program with €1 billion in funding. India created its national mission on quantum technologies, and Japan established the Quantum Leap Flagship program. So the question remains, in this quantum race, will your country lead, follow, or fall behind? So, where exactly are we now? 2025. Quantum computing is no longer theoretical, it's real, and accelerating fast. Google's Willow, 105 qubits, solved in 5 minutes. What would take classical computers 10 septillion years. And more importantly, it cracked quantum error correction. IBM's Nighthawk with 120 qubits pushes toward fault-tolerant quantum computing by 2029, combining quantum and classical systems. Microsoft's Majorana 1 uses topological qubits, error-resistant, scalable to 1 million qubits, backed by DARPA. The market took notice. Q1 of 2025 saw a record-breaking $1.25 billion invested in quantum startups, a 128% jump from last year. Commercial orders up 70%, nearly $854 million in hardware sales. This isn't research anymore, it's business. See, China's ambitions are equally staggering. In 2025, they revealed EZQ Engine 2.0, preparing the leap to over 1,000 qubits. Their latest chip, Zhuchongji 3.0, shattered records in quantum random circuit sampling, outperforming past systems by 6 orders of magnitude. The United States responded. The National Quantum Initiative Act, $1.2 billion for research and infrastructure. And for the first time in history, the United Nations declared 2025 the International Year of Quantum Science and Technology. 2025 marks the emergence of real-world quantum applications. Finance, JP Morgan and Amazon slashed portfolio sizes by 80% using quantum decomposition. Healthcare, IonQ and Ansys accelerated medical simulations by 12%. Logistics, DHL cut delivery times by 20% using quantum route optimization. These aren't promises, they're results. But the revolution needs minds, in classrooms, in companies, in code. The UN's declaration sparked a global wave of quantum education and training, because without talent, all the qubits in the world mean nothing. It's the beginning. No more if quantum will change the world. The future is now.